Welcome everyone. In today's class we will learn DPLL based SAT solver. We have already discussed what is satisfactory problem and what are the different approaches to solve the satisfactory problem. The most popular one is the DPLL algorithm. So, it comes from the innovator name Davis, Putnam, Logeman and Loveland. So, this is the basis of all modern SAT solver. So, you should learn this particular technique properly. Okay. So, this particular SAT solver primarily use that unit clause resolution that I have talked in the previous class, which effectively says that if you have a unit clause L and there is another clause which has say A1, A2, An, but it has not L, right. So, there are two clauses and then what I can do, I can just remove this clause, right, and I can create a new clause which is A1 or A2 or An. Right. So, effectively I will remove this clause, unit clause is already decided, this is the new clause I am going to add, right. So, this is primary resolution method that is being used inside DPLL is this. So, what it does effectively, you have a set of clauses and we assume the formula is in CNF, conjunctive normal form. So, you have to make sure that each clause individually becomes satisfiable. So, what we are doing here is that we basically arbitrarily pick a variable. Okay. It is actually not arbitrary, there are many heuristic which we are going to learn in subsequent classes. So, we randomly pick some say variable and a value, right. So, if the variable you have variable from say A to D, let us say I pick randomly C and assign the value false. Okay. So, once I do this, what will happen if you have a formula let us say A or B or C, right, and you assume C equal to false. So, this formula will reduce to A or B because C become false here. So, once we apply this decision of a variable, the clauses will become smaller, right. Wherever this particular literal occurs, they will become smaller and some of them will become unit clause, right, and that unit clause can be propagated using this unit clause resolution. So, I will keep applying this because if you apply one, some another clause will become smaller, that may create an opportunity of another unit clause propagation. So, this way this process will go and this is called BCP, Boolean constant propagation. So, if I keep doing it, I will reach a situation where I have kind of two scenarios. So, what I decided that I take a decision about a variable and then I will do Boolean constant propagation, and then once I do not have any other possibility of constant propagation, I will go back and take decision about the next variable, okay, and this will open up the BCP again and it will continue. If this process finally if I get assignment of all variables, that is the satisfactory solution, right, but it may not give you the complete assignment, but I may reach in a conflict. It means because I am randomly assigning variable some values and those values may not be the actual value that I want in my satisfactory or that may not able to give you satisfactory, right. So, I may reach a conflict which means that this assignment that I have done so far something is wrong there, and then I will do the analyze conflict, I learn something from there, I will remove some part of my learning whatever I have done so far. So, I backtrack and I restart the process. So, this is the overall DPLL based algorithm. So, what I will do in today's class, I will try to show you each steps in high level, okay, and in subsequent class I will also go into detail about this analyze conflicts and backtrack as well as about the decide. Let us learn some important definition first. So, you know what is clause? Clause is disjunction of the literals. So, a CNF formula has set of clauses, right, clause C1, C2, C3, it may be some A not B not C, C or not D and so on, right, not C and E and so on. So, these are the clauses, it is disjunction of the literals and literals is basically actual variable or their negation. So, these are the literals. So, once I have the partial assignment, because I am talking about I assign some value to some variable, either this clause will become satisfiable, that means this clause become true. Okay. So, for example, if you have the clause A or B or C and if you assign C equal to false, this become satisfiable, okay, because this particular clause become true, right. So, then this is satisfied. It may be conflicting because if you assign some value so that the clause become false, right. Say for example, if you have this clause A or B or not C and say A equal to false, B equal to false and C equal to true. So, under this assignment this will become C1 become false. So, that is called contradiction or conflicting because you do not want that, because your each clause has to be true individually, right. So, this is called conflicting. And then unit clause is that if you assign some values, say for example, say C equal to in this case say A equal to false and B equal to false. So, this clause will reduce to not C. So, this become unit clause because where all literal are assigned, right, only one literal is not assigned and that still the clause is not satisfied, right. See for example, here if you assign C equal to false, then this will become automatically true, right, or A equal to true, this will become true. So, a partial assignment can make the clause satisfiable, a full assignment can make the clause conflicting, or a partial assignment where all literals are assigned, only one is not assigned, but still the clause is not true or satisfied, right. So, then it is reduced to unit clause and otherwise we will say it is unresolved. Okay. Again have a complete example. Let us say I have this assignment x1 equal to true, x2 equal to false and x4 equal to true, and if you have the clause is this x1, x3 and x4. So, here x1 is true, so this will become true. So, this is satisfied. Here x1 is true, so this is false and x2 is false, this is also false. So, this become conflicting because this entire clause become false. Similarly, if you have this clause which has x1 which is true, so this become false, x3 is not assigned, x5 is not assigned. So, this is unresolved, right. This is neither unit clause, neither conflict, neither satisfied. And if you have this clause where x1 is false, x1 is true, so this is become false, x4 is true, so this is become false. So, this reduced to x3, right. So, then this is unit clause under this partial assignment. Also one more definition, antecedent. Once you have a partial assignment and you have a clause, under this partial assignment this will reduce to a single literal, right. So, for example, here x1 equal to true, so this become false, x4 equal to true, this become false. So, this is reduced to x3. So, now I will say that antecedent of x3 is the previous clause, right. So, this because I reached to this single unit clause from that clause C, right. So, the antecedent of this literal is that clause. Okay. Now, let us take simple example and see how this DPLL algorithm works, right. Let us say I have 3 clause here. The first clause has P. So, this is clause 1, this is clause 2, this is clause 3 and this is the unit clause already, right, because it has one literal. So, I try to apply this unit clause resolution, which is that there is a unit clause L and there is a clause where not L present. So, what I will do, I will just remove this not L from there, I will get a new clause. So, here I can see P and not P, right. So, I will put this clause C1 and C2 which will reduce to Q, because this not P will be removed and I will get Q. My formula is reduced to this, right, P, Q and this. Now, you have Q and not Q, right. So, if I put this together, I will get R or S, right. So, I will get this formula, right. So, now you can see here I cannot apply further BCP, but here you can assign P equal to true, Q equal to true, R equal to true and S equal to true. So, this will become satisfiable. So, in the next case, if you take R equal to true, this will reduce to P and Q and true, right. So, this way I will get the solution. So, this way if I apply BCP, I will get a satisfactory solution, right. But you may not always get that scenario. Let us take an example like this. So, this is my clause 1, this is clause 2, this is clause 3, clause 4, right. So, now I do not have any unit clause. So, I have to take a decision about some variable, right. Let us say I decided Q equal to true, this is my assignment. Under this clause will become simplified. So, for example, if you put Q equal to true, this become true, right. So, this become true, Q is true here. So, this become R, right. So, this is R, this become R. this become not q, so not r, because q is true, this will become false. So, this clause become not r, C3, and here this there is no q, so it will be like this. So, after q this is my modified clauses, and I can apply unit clause resolution because r and not r, right. So, r and not r, it will reduce to false because I will remove r, not r, and there is nothing. So, I reach a contradiction. So, what does it mean? The decision about q equal to true is the problem, right. So, the decision that I have taken about q is basically reached to a situation I get a contradiction and I will not get any assignment. So, what I will do? I will basically erase this part of the part and I restart the process with q equal to false. So, if I do that, if q equal to false I write. So, this will become not p r, the first clause, second and third clause become true because not q are present there, and this is become not p not r, okay. And there is no further BCP is possible. Then I will take decision about another variable. This time I take say p equal to true. If I put p equal to true, this is become true, this become r, right. So, now if I put r equal to true, I will get satisfiable. So, this is the assignment where p equal to true, q equal to false, r equal to true is the satisfactory instance under which this formula is true, right. So, DPLL exactly does this, that you take a decision about a variable, you do BCP, if you did a contradiction, that means this decision is wrong, you go back or you erase this part of the decision and then you restart and finally you will get some set. The only things DPLL does, it does not just erase this part and it learns something from this, right. Whatever the mistake you have done here, I learned something from this, and I will discuss that in more detail with a bigger example. Let us take a bigger example now. So, here I have 8 clauses C1, C2 to C8, and I have variable from x1 to x6. I have 6 variables, there are 8 clauses, and each to make this I have to identify the value of this x1 to x6 such that each of these clause are true, right. So, that is the satisfactory problem. So, again here there is no unit clause propagation possible at the start because there is no unit clause. So, let us I have these clauses, okay, and I want to solve with DPLL, right. So, let us say I have taken x6 equal to 0. So, if I put x6 equal to 0, what will happen? I have this clause. So, from there I can make sure that x5 equal to false, otherwise this clause will be. So, this is false means this is false. If I take x5 equal to false, then not of x5 will be true. So, then it will be true. So, this force me to take C8 equal to from C8 that x5 equal to false. Then let us say I have taken x7. So, let us say I have in some clause x7, right, say I have here x7, okay. So, x7 equal to 0. So, this does not help much. So, I take just x5 equal to 0. Then say I have taken x1 equal to 0, x1 equal to 1, right, x1 equal to 1. So, which immediately help me to decide that x3 equal to 1, because from this, right, because you have x1 equal to true. So, this become false, x5 was false, right. So, this is also false. So, x3 equal to 1, right. So, I from C2 I can take this decision. Now, immediately this x2 in this C1 you have x1 equal to 1. So, not of x1 will be false, which will tell x2 equal to 1, right. So, from C1, and now from this if you consider C3, in C3 because your x2 equal to 1. So, this is become false, right, and it basically says that you take x4 equal to true, right. So, your x4 equal to 1, right. Now, if you see here what I am doing here is I am saying x4 equal to 1, right. Now, you think that x4 equal to 1. So, this is false, right, and earlier I have taken x3 equal to 1. So, that means not of x3 is also false. So, this makes C4 is false. So, I reach a conflict, right. So, this assignment x6 equal to 0, x5 equal to 0, x7 equal to 0, x1 equal to 1, then x3 equal to 1, and then x2 equal to 1, then x4 equal to 1. So, this assignment that I got is not correct, right. Because of that I reach one of the clause become false or I reach a conflict. Okay. So, that means some of the decision is here is problem. So, I will basically try to remove some of the decision and I restart the process. Okay. But the information in this particular graph is not sufficient, right. So, I do not exactly find out that this x 3 and this x 4 they combinedly create this problem, right, or what is the order of decision, what is actually BCP and what is the decision I have taken, right. Some of this, for example, this is basically the scenario, this is BCP, right. So, because it is immediately telling me to take this decision, right. So, to store this information we usually use the implication graph. Okay. Instead of doing this kind of a path, what I will do, I will try to construct a graph. So, in this graph I have a set of nodes and set of edges. So, these nodes are nothing but some literal with some decision, right. Say for example, I start with my decision level 0, right. So, initially I will do the BCP at decision level 0. Whenever I take a new variable decision, I will make it decision level 1, right. So, for example, here I take a decision about x 6. So, I will write that x 6 at the rate decision level 1 and but I take a decision 0. So, I will write not x 6 at the rate 1. Okay. So, I basically either I will write x I at the rate DL or not x I at the rate DL. DL is the decision level, and if the value is true, I will write x I. If the value of x I is false, I will write not of x I. Okay. So, this is what I have written here, and the edges is whenever I take a BCP, right, from this node to this decision happen automatically the BCP, then I will write the antecedent there, the clause through which this happens, right. Antecedent I talked about that. If you have a bigger clause and after application of unit clause I get a single clause x, then this is the clause. So, antecedent of x is C, right. So, this is what I will construct, right. So, to explain properly, so I have say x 5 at the rate 1, that means at the decision level 1 I make x 5 equal to true, and if you have a clause like this, so BCP automatically says that it will reach to x 4, right, because you have x 5 and not of x 5 or x 4, right. So, it will basically give you x 4. So, automatically I reach a node x 4 and here because of this clause. So, I will write the edge as this clause. Okay. And now, let us say I have two decision I have taken where x 5 equal to true at the rate decision level 1 and x 4 equal to false at the decision level 2, and there is a clause like this. This leads to a conflict because x 5 equal to true means this is false, x 4 is false means this is false. So, this clause become false. So, this is my conflict node. Okay. So, this kind of edges will come. So, let me take the same example and try to show you what is happening, right. So, what I will do, I will basically take the same example and I will try to construct the same decision whatever I have done here in this, but I will construct the implication graph. So, what I have done initially, I have taken x 6 equal to 0, right. So, I will create a node like this, that not of x 6 at the rate 1, because decision level 1 x 6 equal to 0. So, this helped me to this actually helps me from C 8, it is actually told that you must make x 5 equal to false, right, not of x 5 at the decision level 1, right, because otherwise this this is false. So, to make this must be true. So, x 5 must be false, right, not of x 5 is true means x 5 is false. So, this is what I got. Then I have taken a decision about x 1 which is not related to this is not BCP. So, I take a decision about x 1, but now decision level 2, because in decision level 1 decision is taken, all the BCP is done. So, I will do x 1 at the rate decision level 2, right, because I just have done that. Okay. Or let us say earlier there is one more decision I have taken, that x 7 at the rate decision level 1, right. So, there is a clause somewhere x 7 was there, right, let us say. So, this is what I have taken here also, right, this x 7. So, here I have taken x 7 equal to 0 at the rate decision level 2, right, and it does not impact anywhere, that I have also seen earlier, that it does not impact any of the BCP. So, this is kind of an unnecessary decision. then I have taken x1 equal to 1 at decision level 3. And because of these two, what happened? I have two BCP actually, right. One BCP happened from the C1, right, from C1, because your x1 equal to true. So, this become false. So, x2 must be true. This is at the rate decision level 3. So, x3 at the rate 3 means x2 is 1 because of this, right. I also have one more BCP happen because of this, and this is because of the clause C2. In the C2 what happened? This x1 is true. So, this is false, x5 is false. So, this is also false. So, x3 must be true, right, at the rate decision level 3. So, this is a BCP of these two decision. Okay. Now, immediately x2 equal to 1, it through C3 I will get one more BCP, right, because your x2 equal to 1. So, x2 equal to 1 means this is false. So, x4 must be 1. This is at the rate decision level 3, right, because this is immediately following from this. And whenever this is decision level 3 and 1, so this will be decision level maximum of them, right. So, I have taken about this, and this leads to conflict from C4, right, because what is happening here? C4, x3 equal to 1. So, this is false, x4 equal to 1, this is false. So, I reach a conflict. So, now look into this graph where I do not have those information, how many decisions I have taken, how many BCPs happen, and what is exactly where the conflict happen. All informations are here, right. So, how many decisions I have taken? 3 decisions. One is x6 equal to false, x1 equal to true, and x7 equal to false, and these two lead to some Boolean constant propagation, and finally, I reach a conflict. Okay. So, this is what I learned from this. Now, the point here is that the decision that I have taken about this variable, this x6 or x3, x1, this something, if I do not take these two decision, I would not have come here, right. So, what basically I will try to see what I learn from this, right. So, what I learn from this is one of the decision at least has to be opposite, otherwise I will again always come back to this, right. If my x6 equal to false and x1 equal to true, I will always reach to this conflict. Okay. So, what I learned from this is that either x6 or not x1, right. So, you have to take decision that either x3 x2 should be opposite of this, which is true, or x1 opposite of x1, which is not x1. If I take that decision, I will not come here, right. So, this is the new clause I learned from this. So, this is called conflict driven clause learning, right. So, what I have done here is that my initial two decision, this x1 equal to true and x6 equal to false, lead to me this conflict. So, next time when I take decision, I will never take these two decisions together. So, at least either x6 should be true or x1 should be false. So, this is the new clause that I learned, and if I add it here, so I will basically add this to this, and I will add C9, and I remove this part of this graph, and I restart from here, right, because I will remove everything, I will just restart from this node. Okay. So, this is what DPLL does. Whenever it leads to conflict, it starts see that from where this conflict comes from, and it learn that why this, how can I avoid this conflict, and then using that particular clause, if you add, it makes sure that next time you will not take this decision, right, because this will ensure that both decisions cannot happen together, and hence you can avoid this same conflict in future run. Okay. So, this is what called conflict driven clause learning, and again I will basically discuss this in much detail in the next class. But the second point is that till what point I remove this, right. So, this is the graph I learned from here, and I just say that this is the cut. So, basically what is cut? It is saying that your root node or the decision node and the conflict node should be in other side. In other way, all path from the root node to the conflict node should be go through this cut. So, if I take this, it is making sure that this conflict cannot happen, and if you learn a clause from this cut, it making sure that you never reach to this conflict through the same decision procedure again, right. So, this we will learn in detail in the next class, but once I get this thing. So, I will basically saying that I will now remove all thing. So, I will basically go to the second last conflict decision. So, if you go back here, how many decision was taken? Decision level 1 x 6 equal to false, decision level 2 x 6 7 equal to false, and decision level 3 x 1 equal to true. So, in this conflict this does not contribute, right. So, this is not part of this graph. So, here the maximum conflict is 3. So, what I am saying that second most is 1. So, what I will do? I will remove everything and I will just keep the root node of the second most second last conflict in this graph. What is second highest decision level, right. Why I am doing this? Because this last level decision always leads to the conflict. So, I just remove this part and I just go to the earliest possible, which is the second most decision level, right. Why not the entire tree? Then you have to do lot of rework. What I have done something, I do not want to remove everything and I restart, right. What I am trying to do that I just remove the minimum possible part, which is the last decision level thing, and I learn something from the last decision level and I add it and I restart the whole process by from the second last conflict decision level. Okay. So, in my example the second last decision level was x 6. So, I will basically start from x 6 and I restart the process. So, if I do it here, you will effectively see that this is the conflict that I am going to get. If I can actually show you this. So, you have only node not x 6 at the rate decision level 1 is left out, right. So, immediately from C 8 this is already done last time also. So, not of x 5 at the rate decision level 1, right. This is what I will get. And now I learn new clause C 9, which is C 6 x 6 not x 1, right. So, x 6 not of x 1. So, once I take this decision, this is from C 8 and because your not x 6 is there. So, it will immediately allow you to take another decision, which is basically say not of x 1 equal to 1, right, because this immediate BCP is possible through this, because I have taken the negation is already assigned here, right. Now, from this what I can do, I can basically get one more clause, which is from C 5, C 5 you have x 1 equal to true. So, this is become false, then x 5 equal to false. So, this will become false. So, it will basically say that not of x 2 at the rate decision level 1, right. And then so this is done. So, now this will lead to another BCP through C 6. In C 6 you have x 2 or not x 3. So, not x 2 is true. So, that means this is false. So, it is saying the not of x 3 at the decision level 1, right. And similarly, this also from C 7, now I will get a conflict. Because in C 7 x 2 equal to false means this is false, x 3 not of x 3 is true, that means this is also false, right, because sorry here in C 6, yeah. So, you will take not of x 2 is false. So, this is not of x 3, let us say I have x 3 here. Okay. So, you will say x 3 equal to true, right. So, now in this C 7 I have not of x 3. So, this is true. So, this is false, this is false. So, this is also false. So, I will get a conflict. Okay. So, what I am trying to say that now I learned something, with that I restart the process and I get another conflict. Again what I will do, this is my decision level 1. So, I will remove everything, right, and I learn something from this. So, probably I learn from this that x 2, right, this is the new clause I learned from this. I will talk about why I have taken this node. So, I will now add C 10 that x 2, that means x 2 must be true, and then I remove everything and I restart the process, okay, because this is decision level 1. So, I will go to the root node, I remove everything and I restart from 0th decision level, right. So, this way I will conclude, I will continue, I will get this, and this is the kind of decision graph I have constructed. So, the question here is that we learn the entire process, right, what is happening here. So, one thing here we can learn multiple clause. So, as I mentioned that I learn x 2 here. If I cut it here, I will get x 6. If I cut it here, I will get x 5 or x 1, right. If I cut it here, I will get x 2 or not of x 3, right. So, I can learn many clauses, right. So, what I am saying that there are multiple clause to be can be learned, right. So, here for based on the cuts, which one to pick. So, the answer is asserting clause. So, we will basically pick the one which is called asserting clause, and then how to pick that asserting clause is basically saying that which consists the UIP node, okay, the unique implication point. And how do we automatically get this asserting clause? Here I am just showing diagrammatically, but algorithmically how can I do that? Using binary resolution method. Okay. So, in the next class I will basically discuss all these points, right. What is asserting clause, what is UIP, how to get this asserting clause automatically when a conflict occurs. Okay. Thank you.